So, we are taking AnaCAN Skywalker from them, and our secondary mission was to do an atmospheric analysis. And first up, we would just like to demonstrate how a two-parted CanSat design works.
So the principle is that the CanSat is programmed to register once it passes 500 meters in altitude. And once it's done that, once it gets below 60 meters again, the servo motor will activate, releasing the lander, as you can see here. It worked perfectly yesterday, but we don't have a video to show for it. So.
And now we'll have our data from CanSat, the lander. And on the first graph here, you see the altitude as a function of time. And as you see, the graph starts as the lander is released from the main satellite, so at about 60 meters. And you can see the graph is curving, which means that the lander is accelerating, and that's because it's falling through. And then we have our second graph, which is the velocity as a function of time. And as you see here, the graph is keep growing, and that's because it hasn't reached its terminal height velocity.
Okay, and here we have the acceleration as a function of time, and when the lander is connected to the main satellite over here, the acceleration is constant, and then when the lander is released, the acceleration becomes 0, and that's because it's waveless, and then it falls, and it's because it falls freely, only influenced by the air resistance and gravity. When the descent rate increases, the air resistance increases as well, and the lander will measure a greater and greater acceleration. And when the lander reaches its terminal velocity, the acceleration will be equal to the gravitational acceleration again. And here we have the air resistance as a function of time, and we're able to compare the theoretical one on the left with the practical one on the right, and we can see that they follow each other pretty well. For instance, we can see this on the y-axis, where we have both of them going to 0.4. And there are some uncertainties on the way, and that's can be explained by how we are measured, the theoretical one and the practical one. And the theoretical one is influenced by the measured velocity and the calculated density, and the practical one is calculated by the proper acceleration multiplied with the mass. And here we have the rocket equation, and the theory behind is over here, and that this is the vertical rocket equation, and we have solved it numerically, and we can compare the calculated one with the measured one, and we have made the calculated one as a simulation of how the rocket would be, and over here we have the measured one of how our lander measured both the altitude and the velocity.
Is data from Millennium Volcan. This graph shows the altitude. The CanSat accelerates in the start, and afterwards it becomes more linear, which means that the CanSat is falling with a constant velocity. Our regression shows that the CanSat is falling with 8.9 meters per second. This graph shows the temperature. The temperature starts out high, which could be caused by the heat from the canister. The graph falls drastically when the CanSat deploys, Afterwards, the temperature rises as the CanSat reaches the ground. The temperature is lower than we anticipated, but it develops as we expected.
Yes, to mention that the temperature is a little low, it falls and the measurements it measures below 0 degrees Celsius, which is way lower than what it should have. The problem here may be how we measure the temperature. The temperature is measured by an infrared thermometer, but it points straight upwards. So before the parachute is properly deployed, it might be measuring the air around it. And since an infrared thermometer is better at measuring the temperature of an object, if there's no object it can measure, the temperature would be lower than what it actually is in the surroundings. Then we have the humidity as a function of time. What we see here is that as the altitude increases in the rocket launch, the humidity drops. And once it slowly descends, the humidity increases as well until it reaches about the same value as in the beginning. Only two measurements really sticks out, these two here. Most likely due to a problem with the sensor, but we can't really explain this otherwise. Here we have the measure of the proper acceleration as a function of time. We see there's two peaks, one here where the rocket is launched and one where the CanSat is deployed. Afterward, it should flat out at around 9.8 meters per second squared. We see that it doesn't really flat out, it's a little bit above, around 10 to 11 meters per second squared. And the reason why it doesn't flat out is most likely to because the wind spins the CanSat around, forcing it to measure a weird acceleration. Here we have the air density at different altitudes. We see that we generally have a fair air density, and it increases as the altitude decreases. We have a little high measurement up here, but again the air density is measured using the temperature, and we measured a quite low temperature this high, so that's why we have this unusual peak. Then we have the wind speed at different altitudes. We see once the CanSat reaches the speed of the wind, it generally stays within 10 to 13 meters per second and doesn't really change drastically on its way down. Two measurements sticks out. This is because this measurement over here, the coordinates of the GPS, one of the coordinates didn't update properly, forcing the second one to update twice to compensate for this. So this one is about twice as high as it should be. Here we see the direction of the wind. In the beginning here we have the direction of the rocket, and when the CanSat is deployed, we get the direction of the wind in a cardinal direction. We see generally has a south direction, a little southwest. One measurement sticks out, again that's the one from before where the coordinates didn't update properly, forcing it to measure a little bit more west than it should have. Then we have the 3D graph of the flight. You notice that's a little interesting square going on right here just as the rocket is being launched. This is because the GPS is built so that if it measures a high enough acceleration, it would cease to update the coordinates so that it cannot be used, for example, for guided missiles. Once the acceleration is low enough again, it starts measuring properly and updates. And if we turn it around, we see that it gently follows the CanSat on its way down very beautifully on the landscape here. If we look from above, we will also see that the landing of the CanSat matches where we actually found it, and that the direction of the CanSat matches that of the actual direction we saw in the southwest. So conclusion, we found a way to properly measure the atmospheric conditions, and some things would have to be changed in order for it to be used, for example, on Mars, but we can use these data for numerous things on Earth. Thank you.
Questions? Well, nice presentation. Thank you very much. I'd like to ask you a question about your infrared temperature sensor.
Yes.
How does it work?
Yeah, it works by all objects emit infrared rays once they have a temperature. And the infrared sensor basically uses a lens to concentrate these rays into a little a sensor that converts the energy from the infrared rays to an electrical charge, which it can measure, and using that it gives out a temperature.
Okay, and just thank you. That's a good explanation. But in the negative temperatures you mentioned, you measured. I wasn't just. Could you go through that explanation again?
Yeah. Should I go to the graph?
Yeah.
Here we go. Okay, because the infrared thermometer is pointing upwards, it needs to measure some kind of object to actually see what the temperature is. It doesn't measure necessarily the surrounding temperature. And if it points upwards and there's no object it actually points on, it would just point straight into the air. And there will not be many infrared rays in the air, which means that it will measure a temperature significantly lower than the surroundings. We see that it generally starts increasing here, most likely because it starts pointing towards the parachute instead, and the parachute is a more dense object, hence we get a better temperature, but still it's a little lower than what we would have anticipated. The high temperature in the beginning is most likely due to the canister being warmer than the surroundings.
Okay, so it measures the infrared temperature at a particular distance from the sensor.
Yeah, we're not sure what distance. We actually thought about an interesting experiment would be to use an infrared thermometer on both the bottom and top of the CanSat to see the difference between them. Then we can also tell how far it actually reaches, because that's not an information we have about an infrared thermometer.
Okay, that could be a nice next project. Thank you.
Thank you very much.